property, and then I will introduce a generalization to Banach spaces, representations and Banach spaces. So let me start with the definition of this property, and then I'm going to explain the motivations behind it and what is known about it. So in 2000, from the front, Shalom introduced the following property. Actually, I should say properties. There are two of them, HT and HFD for, let's say, countable. This can be generalized, and I will actually consider generalization to locally compact groups, but for the sake of simplicity now, let me just assume that I have a countable discrete group G. So what is this property? So this property is expressed in terms of unitary representations, in cohomology of unitary representations. So what it says is that G has HT if for all unitary representation phi such that H1 bar of pi is non-zero, pi contains the trivial representation. Or in other words, it contains an invariant vector, a non-trivial invariant vector. And so T, of course, stands for trivial. And if you replace it by HFD, which stands for finite dimensional, then the conclusion, this is the same. The conclusion is phi contains a finite dimensional subrepresentation. A non-trivial, of course, subrepresentation. So what does it mean? So what is what is the reduced cohomology? So let me remind you the definitions. H1 and H1 bar. So this is cohomology. So first I need to define what is a cocycle. So given a unitary representation by H being the Hilbert space of G, B is a cocycle if, what is a cocycle? So B is a map from G to H, satisfying the cocycle relation so this is a cocycle. A coboundary is a cocycle of a very specific form. Here is the definition of a coboundary. Now H1 of G phi is simply the, of course, the, well, one can check that this defines, of course, satisfies the cocycle relation. So this is just the quotient of B1 of Z1 by of Z1 by B1. And H1 bar, the reduced cohomology, is the quotient by the closure. But by closure, I need to explain what it is. It's simply for the topology of the the topology point-wise convergence. Now, if you want to extend this definition to locally compact groups, you just have to assume that the representation is continuous for the strong topology, and that the cocycles are also continuous maps. And then the convergence here is the uniform convergence on compact sets. Okay, so now let me, this is a bit formal. It's formal, but now there is also a geometric interpretation. So geometric interpretation is in terms of affine actions. So if you take, let me maybe write it like that. If you take an element, a cocycle, gives rise to an affine representation of G on H, an affine isometric representation, an affine action on H by the formula sigma of G applied to a vector V is phi of G and V plus some translation part which happens to be your cocycle. So this gives you an affine action. And of course, conversely, if you have an affine action, if you look at the map, the orbit map of 0, the origin of your Hilbert space, it gives you a cocycle. Now, what does it mean for a cocycle to be a boundary? B belongs to B1 if and only if the corresponding action has a fixed point, or in other words, is conjugated by translation, for instance, to a linear action. Okay? And this is also equivalent to saying that sigma has bounded orbits. This follows from the center lemma, which happens to hold true in Hilbert spaces and also in marginal metric spaces or even planar spaces. But in this setting, it's true. And what does it mean for B to be in the closure of the coboundary? It means that it has a sequence of almost fixed points. It means that there is this V1, Vn, sequence of almost fixed points in H, such that for all G in G, sigma of G Vn tends to 0. So this gives you a good geometric interpretation of property HFD. So G has, or HT, if a fine representation of action, isometric action, without almost fixed points, the unitary part has an invariant vector. Actually, one can be more specific because, of course, you can decompose your representation as the trivial one plus the rest. And if your group has property HT, what it means is that the cocycle also can be decomposed, can be projected to the different part of this representation. So what it says actually is that the cocycle, the non-trivial part in H1 bar, is coming from the projection to the trivial representation, which means that it's coming from an action by translation. Because, of course, if the group acts with the trivial representation, then it means that it acts by translation.
Sorry, you said without almost fixed point. Is that
without almost fixed point?
Then
sorry.
There is no.
Yeah, without almost fixed point means that it is non-trivial in H bar. It means that there is a positive displacement. It's the same.
Oh,
that's the same.
Age, Prof, right?
Yes, being non-trivial. So this is being in the B do not belong to B1 if you want. Is equivalent to suppose that G is finitely generated. Then it's equivalent to saying that the displacement is positive. this is the infimum where all V H of the supremum of the maximum, where all S of S. That's another way of saying the same thing. Okay, so, and of course you have a similar statement for J. Okay, so now, let's define this. The main observation of Shalom, or the first observation of Shalom, but let me say the first. Shalom. So as I just explained, if you have property HT, then and if you have a non-trivial cocycle, then it means that there is a morphism to Z somewhere. So this property was introduced by Shalom for this reason. Because property HFD also has a similar, I mean, if you have property HFD and you're amenable, for instance, actually even 18 amenable, and HFD, then it's virtually subjects to Z. So why was it the main motivation of Shalom? Because if you were at Breuer's talk yesterday, he explained that the main step in proving Gromov theorem about groups with polynomial growth is to produce a morphism to Z, or a virtual morphism to Z. Why? Because then you can argue by induction on the growth. You can take the kernel, you can show that the growth is strictly less than the group, and then you can argue by induction. So the original motivation of Shalom for introducing this property was to prove Gromov theorem with a more elementary approach, and actually, and also to prove rigidity statements with a more elementary approach. Like for instance, being quasi-isometric to ZD implies that you're virtually ZD. That's something that you actually proved using this property. And why? Because that's the second observation of Shalom. If G and H are quasi-isometric to one another, and G is amenable, then of course H is also amenable, then H has HFD, if and only if G has HFD. So I'm not going to explain exactly why this is true, but I mean it's definitely not obvious from the definition of property HFD, which is a harmonic analytic representation theoretic definition. So how can you prove such a statement from quasi-isometry? Well, this comes from an observation of Gromov, who observed that if two groups are quasi-isometric, actually this is an if and only if statement, then there exists a locally compact space with an action of both groups which commute. So two actions of both groups. Both actions being proper and discontinuous and co-compact. So you have what is called a coupling space in a topological sense for both groups. But now that we are assuming that one of these groups, or actually both groups, are amenable, then we can actually add a measure to this space. And what we get in the end is a coupling which is a measured coupling. If you're used to this measure equivalence business, introduced also by Gromov, and at the same time a topological coupling. So the topological coupling implies that the measure coupling that you get is actually very much controlled, and you can induce cocycles, for instance. The summability conditions will be automatically satisfied. Okay. And moreover, because it's a measure coupling, you will be able to induce unitary representations. So this induction procedure enables you to construct an affine action of H starting from an affine action of G. And then you can use this business of induction to prove that this property is invariant. I mean, there is some work to be done. It's not completely obvious, but it's that's the strategy. And using the same idea essentially, Shalom also proved that if a locally compact group has property HFD, then all its co-compact lattices have property HFD. And that's another thing which is actually a crucial observation. If lambda is a co-compact lattice in G, and if G has HFD, then so does lambda. I'll come back to that because it will be really crucial for my talk, for the results I'm going to explain. So as I said, I mean, one of the main applications of this property HFD for Shalom was to prove that if a group is quasi-isometric to ZD, then it is virtually ZD. I'm not going to write it down here, but his actual ambition was to produce a new proof of Gromov theorem, and that ambition, he could not really do it himself, but it was concretized by Ozawa very recently, who produced a fantastic proof of Gromov theorem. So Ozawa managed to prove recently, 2015, I'm not wrong, that a group with polynomial growth, by which I mean, of course, that he's only assuming polynomial growth and not that it's virtually nilpotent. So we're starting from the assumption of polynomial growth, has HAP. And therefore, gave a new elementary proof of Gromov theorem, which is different from Kleiner's proof, for instance. And it's completely new. It's amazing. This proof is amazing. It's very short. It's based on random walks. It's very, very nice. Okay, so this is what property HFD is good for. Actually, it's not the only thing that it's good for. There is also you can also use it to. That's something that we've done. It's another application with Cornulier and Valette in 2006. We use property HFD and HT also to prove, in a very elementary way, two statements which are relatively hard to prove. I mean, or at least technically hard to prove. The following things. So one is that, maybe I should change board. So we proved two facts about non-embeddings of groups. So the first one is that non-virtually abelian groups do not quasi-isometrically embed into a Hilbert space, L2. And the second one is that three irregular trees do not quasi-isometrically embed into L2. So this is a result of Paul's in 2001, which is based on a differentiation result of Pierre Consu. He extended it to this setting. And then it was extended further by Kleiner and Schiger. But it's relatively technical. It's not very, very hard, but it's quite involved, I mean, at least for a general nilpotent group. Whereas our proof is nothing. There is nothing there. Like it's extremely simple. And for the triangular trees, that's essentially the same thing. It was a result of Bourgain, which was, at least the original result was relatively involved. Now there is a more simpler proof right now, but, in '86. And we also produce a proof which is completely elementary. I'm going maybe to talk about it a bit later. So, well, just the rough idea behind this thing, of course, you start with a property which seems to have nothing to do with quasi-isometric embedding, because it has to do with affine actions. So what is the relation between them? It's because you have a very nice observation of Gromov that if you have if you consider an amenable group, and if you take for instance, a quasi-isometric embedding into an L2 space, then you can use an averaging procedure to produce an affine action whose orbits are quasi-isometrically embedded in a different Lipper space. There is an ultra product which is hiding behind it. But you can, by an averaging procedure, you can start with something which is not equivariant and produce something which is equivariant. And from there, you can use all these harmonic analytic properties of your group to deduce, for instance, that this is not possible. This is not going to be possible. And that's essentially what we do for both situations. The regular tree, of course, is not a free group because the free group is not amenable, but you can replace it by the lamplighter, for instance, which can be embedded into a product of two free groups. So you can use the lamplighter, which is amenable, to do this kind of trick. Okay, so this was I'm done with the applications. Now I'm going to mention what Shalom wanted to know about it. So what do we know about this property? So which groups, and actually essentially amenable groups, satisfy this property? Well, so Shalom proved that, so even among solvable groups, this is a tricky question. We don't really know, and it could be very restrictive, or it could be maybe not that restrictive. So what Shalom proved, for instance, is that it's an exercise, essentially, Z with Z, so which is an infinite direct sum copies of Z's, together with an action of Z that permutes the various copies of this direct sum, does not have it's not very hard, and essentially you start with an action by translation of this infinite direct sum, each factor translating. So this will not be trivial in the H1 bar. And then you just extend it. You have to show that this is not trivial in H1 bar, but does not have a finite subrepresentation. But on the other hand, if you take Z mod P, this is called the lamplighter. This has HAP. And so based on the result of Delorme, so there is a theorem of Delorme in the 70s, who proved by, studying the Lie algebras and that the following statement connected solvable groups have HFD, and Shalom used that to deduce from the fact that it passes to co-compact lattices. We get automatically for our Shalom that polycyclic groups HFD, and using that he managed to prove something which is a very first step, very initial step, for proving that a group which is quasi-isometric to a polycyclic group is polycyclic. This is a conjecture which is not known. So there is a conjecture that the class of polycyclic groups is quasi-isometrically rigid or quasi-isometrically closed. Virtually polycyclic groups. And so nobody knows how to prove that except for very specific examples, like salt, for instance, but or nilpotent groups. But for a general polycyclic group, it's not known whether if a group is quasi-isometric to it, then it is also polycyclic. But the first step is you'd like to produce at least a morphism to Z or virtually a morphism to Z. But because we know that they have property HFT, and because we know that an amenable group that has HFT virtually subjects to Z, then we get that a group which is quasi-isometric to a polycyclic group at least virtually subjects to Z. That's the very first step. Maybe it sounds a little bit weak, but somehow, I mean, this is really something you want to, this is something you want to start with if you want to go anywhere. So that's not so weak in a sense. Okay, and you can also do these kind of things for other things. So what are the open questions? Open question of Shalom, which is still open, is whether locally finite by abelian, by which I mean extensions of a locally finite group, norms of group by an abelian group, has HFT. And the first example, which is open, for which this is open, this is the Lamplighter with over Z squared, for instance. This group is, I don't know what to believe about this group, honestly. I'd like to say that it doesn't have property HFT, I would prefer it for some personal reasons, but I don't know about it. And the second question that was asked by Shalom, which was, I think, formulated as a conjecture, was whether are solvable. That's a very natural generalization of polycyclic groups, solvable subgroups of GL of Q, HAV. Do they have HAV? Finitely generated. And this has a positive answer, and that's one of the main results I'd like to talk about today. Okay, so now, first thing I would like to mention, which I introduced in the title already, is that there are natural generalization of property HFT. You don't need to work specifically with a Hilbert space. Of course, all the techniques that were used by Shalom, by Delorme, are actually using decomposition into irreducible representations. So if you're going to use that, of course, you're going to be in trouble if you're working, for instance, in AP or something like that. But that's the main point, maybe, of our result here, is that we managed to find, me and my co-author, who I will introduce very soon, a completely new approach for proving this kind of statement, which is very much geometric or dynamical, if you want, in essence, and so doesn't need to use any decomposition into irreducible. And so for that reason, it becomes interesting to consider generalizations of property HFT to more general representations. So we're going to consider generalization to more general non-preserving actions or representations on Banach spaces. It turns out that the right notion, that the right framework is not really to restrict yourself to a class of Banach spaces, but to restrict yourself to a class of representations which are called WAP representation, or weakly almost periodic representations. Representations are non-preserving. Actually, I'm not sure that non-preserving is necessary here. But this representation, they can be just bound. Representations, so G of the Banach space, such that the orbit of every element, for every V to E, the set phi of G to V, when G belongs to G, is, for the weak topology, is weakly relatively compact. So let me mention the two main source of examples. And the reason why this is the right thing to do, to consider. The main source of examples, non-examples, are first where the Banach space E is reflexive. So reflexive, for instance, is an NP space, if you want. Or is strictly between 1 and infinity. And the other example, which you can combine both of them, but the other example is when G acts by measure preserving action on a probability space. And when you consider the corresponding representation of G on L1 of this probability space. This also has WAP, although in general, L1 is not reflexive, and a general representation of G on L1, for instance, if you take G on little L1 of itself, is generally not WAP. But this one is WAP. And this can have some applications, like ergodic theorems, for instance. If you can prove WAP T for a group, you get automatically an ergodic theorem, non-trivial ergodic theorem in L1. It's not completely obvious a priori. Although I'm not going to talk about it today, but maybe good to mention. So, and the point is that why are these representations nice to work with? Is because they have a nice, what is really important for these representations is to be able to complement the space of invariant vectors. Okay, so the main proposition, which originally is due to write it down. Alaouglu and somebody else. I forgot the name to write on the name, so it's Alaouglu and somebody else. So it's from the 40s. And somebody from the 40s. Maybe it was not proved under this full generality, but essentially the proof adapts to this more general setting, is that if phi is WAP, then there is a decomposition of the space of invariant vectors, which I denote by E to the pi of G, which means invariant under pi of G, plus some complement, where W is a complement, meaning that the projection to W is continuous, as well as the projection on E. So the projection whose kernel is this one under this one, you understand what I mean. It's an actual complement in a topological sense. Okay. So this is crucial for our analysis because we want to prove essentially HT. That would be the main point, to prove HT, and then using that some phi index things to get HFT from HT. But HT will be really the crucial thing that we are going to prove. And for HT, you see that you have to deal with invariant vectors, and you like to project your cocycle on the space of invariant vectors and look at the complement and maybe use some ergodic theorem to prove that the other one is going to vanish or something like that. So you really need this kind of property, and this is really the only thing you really need actually.
So W is invariant?
Yes, of course. Sorry, it's a canonical complement. So not only it is invariant actually on the no, it is invariant on the biology. Yes. Okay, so maybe let me first prove very briefly that Z has WAP T. It's easy. We have to start with something. So let me prove it, because it will be somehow a key ingredient. So how do we prove that? Well, we start with an affine action of one element. So you say that T is a generator of Z. Take G as a generator, by which I mean 1 or -1. So now T is unique. I mean, if you consider the literal representation, it's a unique norm-preserving automorphism or an affine transformation. Okay, and so you assume that phi is what? You take the cocycle D, and you want to show that the corresponding affine action has almost invariant, almost fixed points. Okay, and you want to produce a sequence of almost fixed points. So what you're going to do is by constructing this almost fixed point sequence by choosing convex combination of the first element of the orbit of 0 for your affine representation. So you take b of t to the k for t equals 1 to n. Okay. Now you want to show that this is an almost invariant, almost fixed sequence. So you apply sigma of t to v of n minus v of n. Because this is a convex combination, sigma can enter this convex combination. So you've got this. So you can b of t k plus 1 minus b of tk. And you can prove using the cocycle formula that this is the same as now, if you assume that your representation doesn't have invariant vectors, you can always use decomposition, so you can project onto W and consider restrict to the case where phi doesn't have invariant vectors. Then what is this sum? This is just a mean ergodic theorem that implies that this tends to 0. By the mean ergodic theorem, which turns out it to precisely work, to be precisely satisfied for these representations. It's actually the same. Saying that there's a projection on invariant vectors is essentially the same as the mean ergodic theorem. It's a reformulation. So this is really somehow the minimal framework. To get this very first step, maybe that Z has this W, this WAP T property. Okay, so then you can easily deduce from the very similar argument that property W WAP T is invariant under central extension, and so that it is satisfied by all nilpotent groups, for instance. That's very cheap. Don't have to work too much to get that. So essentially a corollary of the proof, or if you want, it's a remark almost. W by nilpotent groups. And from there, you get a very nice corollary, which is not so obvious. You get, again, you get that nilpotent groups, non-virtually nilpotent abelian groups do not quasi-symmetrically embed. I mentioned it along the way because I think it's a nice outcome, which is very simple, into any, for instance, uniformly convex Banach space. Which was known by Chibler and Kleiner in 2005. Again, by these differentiation arguments. So very quickly, how does it work? So as I said before, if you start with the QI embedding, then you, up to changing the space, you get an actual affine action. But this changing of the space may destroy the WAP whatever, or the nice if you start for instance with an L1 or with sorry a reflexive Banach space, this ultra product which is involved in this change of spaces could break the fact that it's reflexive. So you need to start with something which is pretty strong and stable. So that's why you have to assume, for instance, that it's a uniformly convex Banach space, such as LP, for instance, or P infinity. And then, so you apply this averaging trick, which also works in this setting, and so you get an affine action, which has quasi-symmetrically embedded orbits, and then you can apply HFT to show that at some point it produces a morphism from your group to, of course you have to work a little bit, but the proof is very short, a morphism to its Sabinianization, because it takes by translation somewhere. But the fact, but of course then it kills, the fact that it's not virtually abelian implies that this action is actually factoring through its Sabinianization, and so it's not going to be quasi-isometrically embedded. That's essentially the idea, that any attempt to quasi-isometrically embed an nilpotent group tends to factor through the abelianization, in a sense, in a probabilistic sense. So this is the idea behind that, and later I will formulate another result which is also non-trivial. Okay, so the main result I'd like to state is a theorem with Cornulier that we got very recently, that solvable. This answers in particular Shalom's statement, subgroup of GL V finitely generalized has what FD. So the statement in itself, well, answers Shalom's question. So it includes actually. This is true for a much more general class of groups. Much, I don't know, but more general class of groups. For instance, it includes the Lamplighter. It's also, oh, I didn't mention it, but this new property, WAP FD, is also stable under quasi-isometry and passes to co-compact lattices and so on. The same as for HAT. Same proof, actually. Not exactly the same proof, but an adapted proof works. Okay, so why do I mention that? Because, as I said before, this group can be seen as, I mean, it's a subgroup. It's easy to embed it into a product of two trees, quasi-isometrically. Embedded into a product of two trees. It also contains a tree inside. So essentially, asking whether the Lamplighter quasi-isometrically embedded into some Banach space is the same as asking whether a tree quasi-isometrically embedded into a similar class of Banach space. So using this result, we can prove an old result of Bourgain in a very elementary way once again. So we get as a corollary that the three regular tree does not quasi-isometrically embed into a uniformly convex Banach space, which is optimal because we know that it's either an if and only equation. The Banach space is uniformly convex or has an equivalent norm which is uniformly convex if and only if it admits the three regular tree quasi-isometrically embedded copy of the quasi-regular tree. This is essentially due to Bourgain and to Baudier under this more stronger form. And the original proof of Bourgain is quite involved. It's using some variety theorem of Pizier, and it's not really an easy thing. Later, it received a more elementary treatment by Naor and his co-authors. But it's still, I think, more complicated than this proof, which is very, very simple in a sense. Okay, so I'd like to maybe say a word about the proof because the proof contains some intermediate steps which are maybe even more interesting than the result itself, at least for some of you who are interested in the structure of solvable groups or so the idea behind all of this is to first start with a new approach for proving property HFD or its Banach version. And the class of group for which this idea works pretty well is not the class of discrete groups. We do not have any direct proof actually of property HFD for discrete groups. The only person who managed to do that is Ozawa for group with polynomial growth, or he's not using any only random walk and stuff like that. He's the only one, the first one, who managed to prove HFD by discrete means. Otherwise, all the proofs that we know, Shalom's proof for any example which is known, except for nilpotent groups, of course, uses some kind of local compact, some crucial features of locally compact groups. Like for instance, the Delorme's result. So here, that's the same thing. We are also using some non-discrete features of certain class of groups. And so the first step, if you want, the first step of the proof is to prove W WAP T or WAP T for a class of solvable, locally compact groups with nice, I'm going to make this very precise, dynamical properties. And the second step, which may be more interesting than anything else here, I don't know, is to prove that a solvable subgroup of GL of Q happens to be a lattice, a co-compact lattice, in one of these groups, which looks pretty much like, but it's not exactly this, but it looks really like an algebraic group, if you want, solvable algebraic group over a product of local fields, like QP, R, essentially. But it's not exactly that. Otherwise it would be easy. You would just take the Zariski closure and you would be done. Of course, this is not that simple. And then, even if this class of groups is relatively nice, you still have to work inside to understand that you have all the ingredients to prove your properties. And actually, many more properties. Once you have this, you can prove many, many things for these groups, these subgroups of GLN of Q, things that were not known until now. So that's why this result is interesting in itself. Okay, so let me, in order to illustrate, I have still 5 minutes, to illustrate what I mean by dynamical properties, I will explain to you how to prove this property, WAP-T, for a very simple example, for which all the IDs are already there, namely the affine group. We could do it on QP, or here we're going to do it on R. So illustration of these nice dynamical properties on the following example. Let me call it AR, which is the group. I should take R here, but I'm just going to simplify it, just take Z. Well, Z acts by powers of 2. So what's the nice dynamical property? Of course, it's obvious. Z acts contracting R. And of course, you never see this kind of thing in a discrete group. Of course, you never see this kind of contraction. So what's going to happen is that I'm going to prove this property HFD, and what's going to happen actually is that this Z will be the only one somehow to matter in this situation. The R being contracted will always kind of collapse, will never show up in a sense. It will always hide itself. Z will take all the, will be the important one. So the first observation, oh, well, I need to explain, so T will be the generator of Z. The generating set, compact generating set will be, I will take -1, 1 cross, well, T plus or minus 1. This would be my compact generating set. And, okay, so now the first observation, well, maybe I should mention also the statement. So, proposition, AR has what T. I'm going to prove it. So the first observation is that GR, or ARC, has a sequence which we call, in a non-paper with Cornulier and Valette, we call them control formula sequence. Sequence Fn of compact subsets, such that the supremum over S is S of the size of Fn of the symmetric difference of Fn, which is translated by S divided by the size of Fn. Is less or equal than a constant divided by n. That's the first estimate. So it tells you it's a Furner sequence, but with a certain decay. And then the control is on the diameter. Fn is contained in the ball of radius n, S to the Cn. So this, you can never beat that. Okay, this is the best thing you can expect for a Furner sequence. You cannot have this decay and being contained in something which is smaller than the ball of the other of it. It's very easy to check. It's just triangular quality. So that's the best you can expect. And also, why is it the case? So indeed, and that's an easy exercise to check, that if you take Fn to be, for instance, -3 to the n, 3 to the m, like a big cigar, plus minus mn, here it's in Z, here it's in R, then they satisfy this property. It's quite easy to check. I mean, it's clearly contained in the of order n, let's say 2n, for instance, because you can use the dilation by Z to get the ball of this, to get the interval of size 3 to the n. Okay, and it's also easy to compute the size of the boundary, which essentially amounts to showing that the only thing that really matters is the boundary with respect to Z. This one kind of does not show up in the sense, or it's completely negligible in comparison. So again, it means in the sense that the fact that they have control sequence comes from the fact that it's only Z that matters here. Now the second observation is quite easy. I'm not going to prove it because I don't have time, but it's an observation that we made again at that time, is that a cocycle B is trivial in H1 bar if and only if it is sublinear, namely if sorry, so for I forgot the assumption. So if G has control on a sequence, then this is true. The triviality of a cocycle can be seen is equivalent to this dynamical criterion, namely that the orbits are curved in a sense. They are not quasi-isometrically embedded. Actually, much more than that. They are really curved. uniformly. They cannot be, so they go sublinearly. Okay? This is an if and only if. One direction is easy and always true, but the fact that the other direction comes from the fact that you have Fourier sequences. The Fourier sequence allows you to construct almost invariant, almost fixed points, as you may guess. So, okay, so what else? There is a third observation, which again tells you that Z is the only one that matters here, is that if G belongs to AR, then there exists, you can write it as T minus N X Tm, where X belongs to minus 1, 1, so it belongs to the generalizing set. N, let's say, is positive, and you have that N plus M is less or equal than the size of G. So what does it mean? It means that essentially you've written down your elements writing with the action of Z. The R part is just this X that doesn't move, which lives in the compact space. So what's the consequence of this? If you combine 1, 2, 3, what you get is that B, a cocycle, is trivial in H1 bar, if and only if B restricted to Z is trivial in H1 bar of pi restricted to Z. Why is that? Because Z, of course, has control Fourier sequences. So for both groups, A, R, and Z, being trivial is equivalent to saying that they are sublinear. Okay. But now, because you can write any element like that, you see that if you know that your cocycle is sublinear in restriction to Z, then it will automatically be sublinear in restriction to G, just using the cocycle relation in a stupid way. Okay? So it tells you essentially that only Z matters. Now there is a very last observation, which is that pi has AR invariant vectors if and only if it has Z invariant vectors. It's like a Mortimer phenomenon, if you want, but easier. And moreover, if you have a vector which is Z invariant, it is automatically AR invariant. Why is that? Let me do it just in a Hilbert case. So suppose that E is a to simplify. Then what you write, you just write pi of. So the only thing you need to check, because it's Z invariant, is that it's also R invariant. So you take X in R, and you take P of X VV, the inner product. Then, because it's T invariant, it's the same as P of X, pi of X, pi of T to the N for some N V, pi of T to the N V. You put the pi of Tn on the other side. You get pi of T minus N X Tn V V. But when N tends to infinity, this tends to 1. So it tends to 1 as T goes to infinity. Of course, V was unitary. So this implies that V is invariant. Okay. That's it. So once you have that, you have essentially that the property HT or property WAP T for AR is just following stupidly from the fact that Z has property WAP T. Okay. So I'm almost done. That's the proof. Conclusion. WAP T for AR now follows from for the subgroup Z. Okay. now I'd like to make precise this statement about this family of groups for which we can prove property WAP-T and property WAP-FD, because maybe it's interesting to understand what kind of groups will be realized as co-compact envelopes of this family of groups, GLN of Q. So the theorem A, if you want, well, sorry, before quoting the theorem, so let me introduce the definition. So it's an ad hoc definition. But, so G, locally compact, is of class C if G equals U times N, where, and there is a list of properties, U and N are closed. U is closed, of course, and normal. N is compact by nilpotent. U is an algebraic unipotent. Think of unipotent matrices, subgroup, or isomorphic of GL of a product, a finite product of local fields. Not necessarily of zero characteristic. And the last statement is the most important one. It tells you the dynamical property that you need. U is can be written as a product, finite product of subgroups V1, Vm, such that for every I, so these are subgroups, there exists T in M, such that Vi is normalized and contracted. By T. Contracted meaning what we had above. I mean that the conjugation by T maps everything to 1 asymptotically. So once you have that, then you can prove that you have WAP-T. And if you take a slight generalization of these conditions, you get WAP-FD. That's our main theorem, which is based. Of course, you have to prove that you have further sequences, and it's not so hard. It's not so easy. You have to prove that you have this nice way of writing an element using only n, and that's not so easy either, and so on. But essentially, the proof otherwise is the same as this one. So the theorem A, Romain Tessera, is that groups of class C have WAP-T, and I did not introduce it, but there is a slightly more general class which I call C prime, which has WAP-FD. An observation is that solvable connected groups belong to C prime, and that solvable algebraic groups over QP belong to C. Also. So it gives you, for instance, that this class has WAP-T, which is not which is known, which is new. It's not obvious a priori. It was not known, even for HAB. And then the second theorem, of course, as you may expect, is that subgroups solvable, and then I will stop, solvable subgroups of GN2 have co-compact envelopes in C prime. combining all of these, you get the results. Thank you for your attention.
So we have the last condition on the bottom here. Means that each factor contracts one element of n.
So it's not necessarily a factor, and when I write U as a product, it doesn't have to be a factor, it's just generated somehow by product. It's not generated by, but any element can be written as V1, V2, Vn. Bounded number of terms.
It's pretty weak assumption, right?
It's relatively weak in the sense that it's satisfied by a large class of books which kind of are of this type. What is not so easy to get is to get this kind of almost split thing, because you need this group N. It's almost a splitting of U inside G. In this you have to work a little bit to produce this kind of thing. I didn't say maybe, no, N is compact by nilpotent. So the idea behind this is that N being compact by nilpotent, it has WT, and because of the contraction business, it's only the N that survives whenever you apply any argument. N is the only one to play a role here.
Right, so U is nilpotent, but
Yes.
N is not.
N is compact by
But
nilpotent.
compact, again, and contracts. Yeah.
Sure, I can give you a very simple example, which is not completely obvious already. You take R, you take Heisenberg.
It's not true that every solvable Lie, for instance, satisfies this.
Yes, it's true. That's what I said.
In
So
the legal
not exactly that. You need to modify them a little bit. You have to take a co-compact. You need to increase them a little bit by adding a compact group and then take a subgroup, which is co-compacting. So if you take Heisenberg with so it's this one is X, where you see the action of Z being by multiplication by exponential T here, exponential magnitude here, and trivial on Z. Here you see that V1 will be the group R generated by X, Y will be V2 will be the group generated by Y. But you see that to get Z, you need to take a product, take a commutator. You need to take V1, V2, V1, V2. So there is repetition, if you want, sometimes in this product. I'm not saying that these are distinct. You could take many times the same one. In this case, you need to do that. Because the action on Z is trivial here. It's not contracting there.
Romain,
Yeah.
in theorem B, do you want to restrict to finitely generated groups? Or?
Yes. I didn't think about the non-finitely generated case. Maybe you can do something as well. They will not belong to this class. Actually, I didn't mention it, but this class, I should say that they are compactly generated. In the assumptions, class C are they are supposed to be compactly generated. I forgot to mention it. It's probably not necessary for the conclusion.
Right, but in the class C, these groups are not compactly generated.
They are well, they say that they are. They say that they are. It's safer. You don't need it actually for the conclusion to hold true. It's compactly generated. Sorry, I forgot to mention finitely generated here, but it's safer also. I didn't think about the case where they are not finitely generated. I think it's still okay, but I didn't think about it. I feel safer assuming that they are finitely generated.
Yeah. And of course, I'm bound to ask, what about other finitely generated soluble groups of finite rank?
Yeah, it holds true as well. I just wanted to keep this as elementary as possible, but the statement, the property is stable under taking quotient because of your results. It's true for all finite rank.
But is that then an application?
It's an application of the results. Yeah, I should mention it for that reason.
No, it's not that you should have mentioned it. It's just I'm thinking, there's really no direct proof that just.
There may be a direct proof. We actually, as we talked about, there may be a direct construction of a co-compact envelope for these finite rank groups.
Yeah.
Although this is not the way we did it, was really by starting with taking the Zariski closure, blah blah, and then trimming a little bit. And
Well, we should talk about that.
we should talk about it.
Okay. Right.
The passage from HT to HFD. So how does this happen?
Well, what happens is that what we really do is proving HT for the class of group class C. Then the class C prime happen to be groups which are differ from a group of class C by the fact that they are co-compact, that they contain a co-compact subgroup which is in class C, for instance. So you need some induction, but the induction loses property HT or WT. The induction process, you get a compact group acting somewhere, and then you're left with some, you have to use Peter Weil, and you have finite dimensional representations, and no longer trivial ones. So that's why it's for the, and actually the property HT is false for connected eddy groups in general. And for polycyclic groups as well.